right, good morning. So today I would like to start talking about chapter 9, which is called Chemical Bonding 2. And what we're going to do is we're going to look at a couple of different models of chemical bonding. This is chapter 9. So in chapter 8, we looked a lot at Lewis structures. Lewis structures is a pretty useful method for thinking about chemical bonding, but we're going to look at some more advanced or at least slightly different models of how we think about the covalent bond. The covalent bond is so important in terms of our understanding of organic compounds that it's important to be able to develop theories that explain the behaviors of the molecules and the compounds that we're making. So Lewis structures goes so far, it does certain things that are pretty good. The octet rule is pretty useful. Things like formal charge and resonance are good ideas that are very helpful. But we want to now look at what's called molecular geometry. And really, in a sense, Lewis structures don't have much to say about that. So we'll call this geometry or shape. Okay, what's the shape of a molecule? So when we think about compounds like water and such, we have some sense that molecules have shapes, right? So what we want to do is we want to come up with a theory that can kind of explain that idea. So let me bring up here a little water molecule. And take a look at this. So here is an image of the shape of water. And there's a water molecule right there. Okay. And so notice we have the oxygen at the center. So that's a central atom. And then we have two hydrogens, but notice the angle between the hydrogen atoms. It's not 90 degrees, it's not 180 degrees. So it's not a straight line or a right angle. It's 104.5 degrees. And so that's a little more than a right angle. Remember, 90 degrees is a right angle. And then we have our slight negative charges on the oxygen and slight positive on the hydrogen. We'll talk more about that in section 9.2. So what we want to do is we want to have a model or a theory that can help us describe why water has the shape that it actually does. And the simplest theory that we have for describing that is called the Vesper theory. So I'm going to write it out. It's called valence shell electron pair. It's a big name, repulsion. Okay, and this is a theory. We're going to give it an acronym, VSEPR. And typically people will call this Vesper. VSEPR is Vesper, okay? And this is the theory that we'll talk about now for describing the shapes of molecules. So this is used to determine the shapes of molecules. And it's not perfect. It doesn't work for everything, but it works for a large class of molecules and compounds. So it's a useful theory. And it's also based essentially on the Lewis structure. So it's an extension of the Lewis structure. So that's a good thing too. That way we don't have to relearn everything, right? Some of it's consistent with that. So we're just going to add on a couple of things. So here's how it works essentially. Essentially what we do is we analyze the Lewis structure. So we have a Lewis structure, and then what we do is we count what are called electron groups. Now the term groups is used, also the term domains is used. Okay, so you'll see that on, depending on where you look, you'll see either groups or domains. I think Alex uses the term groups, but A lot of textbooks will use the term domains. Okay, so here's how you do this. What you do is this is around the central atom. So you're just looking at the central atom. Okay, as the molecules get more complicated, then you can have more than one central atom, and that's fine. You can analyze that too. But we'll begin just by looking at the central atom. So imagine the central atom, symbol A. Okay, we'll use that as a generic central atom. And it's surrounded by some number of surrounding atoms. Okay, and I'm just going to make up, a double bond there, a single bond there, and then I'll put a lone pair on the central atom. Okay, so again, we're just considering the central atom. Here's what you do. You count what are called electron groups. Now, an electron group around the central atom is any type of bond. It could be a single bond, it could be a double bond or a triple bond, but one of those counts as one electron group. So a single bond counts as an electron group. Okay, so a single bond, remember, we represent that using the line notation. That's one electron group. A double bond counts as one. Okay, so we're not counting bonds, we're counting arrangements around this atom. So a double bond counts as one electron group. And then we have a triple bond. Same thing, counts as one. In addition to that, a lone pair around the central atom counts as an electron group. So let's count for this one over here. We have one lone pair, so that's one group. We have one single bond, that's a second group. And we have one double bond, that's a third group. So we would say there are 3 electron groups around the central atom. Okay, so you're counting the number of groups. So let's look at an actual molecule. Here's one right here. I'll do expanded octet here. So this is a messy one here. We've got a lot of lone pairs to draw in here. Okay, so again, from the perspective of the central atom, you're just looking at the central atom. Don't worry about these lone pairs on the surrounding atoms. Those are not related to this theory at all, really. So what you do is you count up the number of bonds. So there's a single bond there. There's a single bond there. These are all different single bonds. So it looks like we have 5 electron groups. Okay. Now, there's a notation that we use with the Vesper theory, and the notation, and again, this varies depending on who's doing it. I'm going to use X as the symbol for the surrounding atom. Some people use a B. Either way, what you do is you write the symbol for the central atom, then the symbol for the surrounding atom, and then there's some number of surrounding atoms. Could be 1, 2, 3, 4, 5. So you put N for the number of surrounding atoms. And then you write an E. And I'll use a different symbol, M. E represents lone pairs. Oops. On the central atom, right? Only on the central atom. We're not concerned about the surrounding atoms. And this is the number of lone pairs. So if it was just one lone pair, just write E. If it was 2 lone pairs, it would be E2. And so that's the notation that we're going to use for this. So let me show you an example of this. Let's try, let's try NH3. That's a simple enough one. Okay, so first you draw the Lewis structure. So nitrogen's at the center, 3 surrounding hydrogen atoms. Okay, so that's your first step. You'll find in this chapter, really the first step for many of these things that we do is to draw the Lewis structure. So you draw Lewis structure, there you go. And that's not done though, right? We have to count for the electrons. So nitrogen has 5 valence electrons, and then hydrogen has 1, so that's a total of 8. We've already drawn in 3 bonds, so we'll subtract 6. So we need another 2 on the nitrogen, and that gives us 0. So there's our Lewis structure. That's your starting point. So now let's draw the notation here. The central atom is nitrogen, so A. There are 3 surrounding atoms, 1, 2, 3, so X3. And then there's 1 lone pair on the nitrogen, so that would be E. Sometimes people will put E1. That's perfectly fine. It's not a chemical formula, so you can put 1 there if you want to. But that would be essentially the notation that we're looking at for this particular molecule. Let's look at another one. Let's try, for example, P. Do you want to do PF3? Let's do PF3. There we go, PF3, okay? Well, first of all, you know part of it already. You know that it's got a central atom and 3 surrounding atoms, so you've got that. The only question is, does it have any lone pairs? Are there any lone pairs of that? So how do you figure out if it's got lone pairs? You got to draw the Lewis structure, right? So let's draw the Lewis structure for this one. Phosphor at the center, 3 surrounding fluorines, and then you go through all the electron calculations, right? Phosphorus has 5. There are 3 fluorines. Each fluorine has 7, so that's 21 plus 5 is 26. We've already drawn in 3 bonds, so that's 6. So what do? You get the surrounding atoms up to 8. And then if you have any additional electrons, you put them on the central atom, get it up to 8, or even more than 8 sometimes. So I just put in 18. So I got 2, so we put it right there. And what you're going to find is that the notation that we're using for Vesper theory is pretty much the same for PF3 as it is for NH3, even though the phosphorus is a different element. You have a central atom, 3 surrounding atoms, and then 1 lone pair on the central atom. And you can put E1 or E, either one. Okay, so that's the notation that we're going to use. Now, the reason we focus on this notation is because there's a bunch of different shapes that are possible, a bunch of different geometries, and it's useful to have like a notation so that you just know the list. And that's essentially what we're going to do. We're going to make a list of these, okay? So I'm going to do my first list. So this is list 1. And this is the ones where you've got A, X, N, and there are no lone pairs on the central atom. Okay, and then I'll make a second list where there are lone pairs on the central atom, at least for a couple of them. Okay, so the first possibility would be just to have AX2. So if you have 2 surrounding atoms, and then 3 surrounding atoms, and then 4 surrounding atoms, and then 5 surrounding atoms, and then 6 surrounding atoms. Okay, and then we don't need to go beyond 6 because it turns out crowding in more than 6 surrounding atoms on 1 central atom is very challenging geometrically. There's just not enough room for it. So here's what happens when you do these. You get these particular shapes, and you're going to need to memorize the names of these shapes. The first one is linear. The second one is trigonal planar, AR. The third one is tetrahedral. The fourth one is AX5, is trigonal Bipyramid. And then the last one's called octahedral. And there are angles that you want to memorize as well. So the angles are 180, 120, 109.5. This one has two angles. It's 120 and 180. And then the last one is 90. Okay, so the particular formula, AX2, AX3, AX4, linear, trigonal, planar, tetrahedral, trigonal bipyramid, octahedral, and then 180, 120, 109.5, 120, 180, and then 90. You want to memorize that chart. Okay. Now, what I want to do is I want to show you the shapes that correspond to these arrangements. So let me bring this up. Here we go. Okay. Okay, so here are those shapes that I just put in there. There's one extra in here. We're going to talk about that separately. But the 5 that I gave you, the first one was linear. And this gives you sort of an arrangement right here. It's linear just means a straight line. So the surrounding atoms are just straight across from each other through the central atom. The second one, trigonal planar. Now this one is two-dimensional, right? So when you have something that's two-dimensional, like a piece of paper, right? It's flat, and you can rotate it in and out like this or this like that. So how do you represent it? What they're doing is they're showing you a particular notation here, which is called the wedge and dash line notation. So when you have a wedge like this little bold triangle, that means that it's coming out toward you ever so slightly. And if you see the dash line, that means it's going away from you. So this representation here, imagine that the screen is a flat piece of paper, which it essentially is, right? So if you draw a straight line, that's like a straight line. And then imagine this atom is going into, like beyond into the paper. And then this one is coming out of the paper towards you. Okay, so like a little V, right? The V, you know, from my perspective, this one is coming toward me, this finger. This one is going away from me. So the going away from you is the dash, and the one coming towards you is the solid wedge. Okay, so it's two-dimensional. We're going to skip this one for right now. We'll come into this one later. Now let's look at the tetrahedral. This is the 109.5 degrees. So the angles here are, you can see those angles, you know, they're, again, we're trying to represent things that are more complicated on a piece of paper, but if you can visualize it, it's helpful. So this is the tetrahedral. So this is our AX4. And so what you get is like a little triangle, a little puckered triangle down here at the bottom, and then a fourth one coming up like this. And this is called tetrahedral. Okay. Trigonal bipyramid. Now notice they put AL at the end. That depends on the people. There's no absolute, I mean, actually there probably is now through IUPAC. Different people will modify the names of these things, unfortunately. So some people will call them trigonal bipyramidal. Some people will call them trigonal bipyramid. Some people will call them triangular bipyramid or triangular bipyramidal. It's unfortunate, but for some reason it has not been locked down. This is the actual name. Let's not change and vary the names. People will use slightly varied names, but it's trigonal, meaning a triangle, and then bi, meaning two, and then pyramid. So essentially what you get here is a pyramid, and then there's two pyramids. So imagine coming down like this, and then this is coming down, going up to like that. Okay, so that's got 5 atoms. So notice this, notice I said with this one, there's 2 angles. There was 90 and 120. So the 120 is here in the center. These are 3 central atoms. I'm sorry, I'm using bad notation. These are 3 surrounding atoms that are attached to the central atom that are in the middle. And so we call them equatorial. These are called equatorial atoms, and they're in the center. And then you've got these two that go up and down. These ones are called axial, A-X-I-A-L. So there's like an axis. So you can almost think of it like a globe, like of the Earth. You've got the equator at the center. So these are like a belt in the center. And then you've got a North Pole and a South Pole. These are the axial positions. And so we're sort of thinking of it sort of like this. The idea is you got the central atom, and then each of these surrounding atoms are just attaching to these points. So there's 5 points for this one. Here there's 4 points, and there's attachments. And here there's 3 attachments. And then here there's 2 attachments. So the surrounding atoms are just attaching to the central atom on these positions. And if there's 2 positions, you get a linear. If there's 3 positions, you get a trigonal planar. If there's 4 positions, you get a tetrahedral. If there's 5 positions, you get a trigonal bipyramidal. And then if there's 6 positions, you get an octahedral. So notice the octahedral is 90 degrees. Again, sometimes it's a little hard to see this, to visualize this, but with 6 attachment points, and each attachment is the same distance from all the others, you get 90 degrees. So it's 90 degrees from like a little right angle here. So from here to here, it's 90. 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 And then from these ones, 90, 90, 90, 90. And then these ones are actually 90 because it's like a little square in the center. Again, these are called equatorial positions. And then these are called axial positions. So that one has 6. So there's only one angle. You could say, hey, look, it's 180 to here, half of a circle, but generally we're saying to the nearest one. To the nearest one is 90. Whereas here, to the nearest is 120, but to the nearest here is 90. Okay, 90 to here, 180 to there. Again, the notation is a little awkward. You just have to memorize it. So linear 180, trigonal planar 120, tetrahedral 109.5, a little more than a right angle. Trigonal bipyramid, there's 2 angles. There's 120 for the equatorial positions, and then either 90 or 180. So some people, they measure down to here. Some people measure all the way to down there. Okay. Unfortunately, as I said, you'll see this a lot in chemistry. It just ends up being a cultural phenomenon. People call things whatever they feel like calling them. And so there's slight variations in terms of what we name things. Octahedral right there, AX6, right? So those are all the ones without any lone pairs, and you just sort of memorize them. You memorize the names of them, you memorize the angles, and you practice drawing them. So just on a piece of paper, you just draw these things. Do the dashed and the wedge, the dashed and the wedge. And this is really, in a sense, something that you'll start off very early on if you go on to take organic chemistry. It's something you do sort of in the first week, is practicing drawing these, because if we want to understand the chemistry, the reactivity of these substances, we want to be able to draw them so that we can draw little pictures to show ourselves what's actually happening. Okay, so those are common, it's kind of nice down there. It says common molecular shapes, right? And that's exactly what those are. Those 5 are common molecular shapes. Now I want to show you these 2 over here. So that's going to be our second list over here. And let me show you those. Okay. So I'll call this list 2. And these ones are the ones that have lone pairs around the central atom. Okay, so AXN, EM. So I'm going to sort of limit this. I'm not going to go through all of them, but there's a bunch of them. But let me start with the 2 most important. The first most important one is called bent. And this one has an angle of, I'm sorry, let me write it over here. Actually, let's come back over here. So AX2. And then E2. Okay, that's the most important one. This is called bent, and the angle is 104.5 degrees. The next one is also bent, but it only has one lone pair on the central atom, but it has a slightly different angle. It's closer to 120 degrees. So it's actually the same angle as trigonal planar, but it's actually called bent. And then the next one is AX3E1. And this one has a fancy name, Trigonal Pyramidal. Okay, and this one is 107 degrees. Okay, so there's three. Let me show you one more. AX4E2. And this one's called square planar. And it's 90 degrees. Okay. There's a few others. There's one called a seesaw. There's another one called T-shaped. And there are even some other shapes that have the same name, but they have different arrangements. But these are the four most important ones for the ones that have lone pairs on the central atom. So let me show you the first three of them. We'll come back to this one. This is actually pretty nice. So we're going to look over here at these two. So see, even this one, sometimes people call it, I've actually heard the bent called V-shaped, as in Victor. I've heard it, and here it's called angular also. So again, sorry about it, but it's just people want to make up these names and they just will not, chemists are not that good at agreeing on things. And so they're going to insist on using the name that they came up with. And so you have bent or angular or V-shaped. So notice what you have here. You have two surrounding atoms, right? So AX2, and then you have lone pairs, two lone pairs. So there's your E2. And that angle between the surrounding atoms is 104.5 degrees, okay? Now, if you look over here at the trigonal pyramidal, AX3, you've got three surrounding atoms. So it looks like a little pyramid, right? And you have one lone pair. So there's your E. So this is AX3E1, 107 degrees, okay? So almost the same angle, 107, 104.5 is that angle right there for bent. And then the other one I said was that if you had one lone pair, so there's only one lone pair, then the angle's a little bit bigger, it's 120. So it'd be just like you got rid of one of these E's. This E right here would pop up a little bit further up here. These X's would spread out a little bit and you'd be at 120 degrees. Okay, so those are some of the common ones. Square planar is also a relatively common shape. That one just looks like a little square. So let me show the square planar for you. So this is what you get when you have AX4E2. So essentially what you get is the central atom, and then I'm going to use the dashed wedge. And then you have your E, your lone pair here, and your lone pair there. So what you get is a little square planar. Planar just means flat, right? Two-dimensional flat. So this is your square planar that you get right here. Okay. And then those are the ones that I wanted to show you. There are some others in there as well, but those are the kind of most common ones. Now, before we move on to actually looking at some of these problems, I want to show you what the basis for this theory is. Valence shell electron pair repulsion theory. VS, valence shell, EP, electron pair, R, repulsion. So here's essentially the idea. Remember that electrons tend to form pairs, right? Why? Because when you have a atomic orbital, they tend to go in two at a time, right? So each orbital is going to have a maximum of 2 electrons, right? This is back from chapter 6. So let's say, for example, we've got a 3p subshell. They tend to go in pairs. So they tend to pair up. Quantum mechanical phenomenon. Pauli exclusion principle, right? So the question then is, you know, can you use that idea that they form pairs to describe the shapes? Now let's remind ourselves that electrons have negative charges, right? So even forming pairs, there's a little bit of a contradiction there, right? Like you're saying, hey, they're negatively charged, but they're going to occupy the same space. That's from an electrostatic perspective, we might not expect that. But it's a quantum mechanical phenomenon that they will form pairs. So it overcomes that what we call a Coulombic repulsion, that they tend to push each other away. However, what we're claiming with Vesper theory, VSEPR, is that these pairs of electrons, okay, so there's a pair in an orbital, right? So this is just a generic orbital, right? I'm just going to draw a little bulb there for a generic orbital and indicate that there's 2 electrons in it. That what happens is these electron pairs will repel each other. There's a repulsion between the pairs. Now, even that is technically incorrect. What we're claiming is there's a repulsion between groups. Because remember, we said you could have a double bond or a triple bond, and that counts as one group. So really, the repulsion is between the groups. Okay, so let's imagine that you have 2 single bonds to a central atom. Like in water, right? Water has a single bond to each hydrogen atom. There's going to be a repulsion between those bonds. The bonds are repelling each other, but really it's the groups. And so when they repel each other, the argument is that those orbitals will move as far apart as they can geometrically to minimize the repulsion. You can see right here that they're not as far apart as they can get. So what'll happen is, you know, there's no good notation really for this, is that they're going to look something like this. They're going to move as far apart as they can. And that would be like that, right? That's about as far as you can get from each other. And so then the argument is that then you just attach your surrounding atoms. So really what's driving this theory is the orbitals themselves are moving away from each other, and then the surrounding atoms are just attached like little balls at the end, okay? So how do you minimize repulsion? You minimize it by moving far away from each other, right? So think of, you know, almost like in a subway, if there's a bunch of empty seats, people will often sit away from each other. So they're repelling each other in some sense. So they take opposite seats, right? They might even be on opposite sides of the car, okay? That's essentially what these electrons are doing. But they're doing it not as individual electrons, they're doing it as groups of electrons. A group is a lone pair, a group is a bond, a group double, and a group is a triple bond, okay? So let's take, for example, water. Again, the idea is you draw the Lewis structure. Okay, so there's the Lewis structure for water. So how do we analyze that in terms of Vesper theory? Well, what you do is you say, hey, look, you've got this central oxygen, and then you've got 1, 2, 3, 4 electron groups. Remember, a lone pair is a group, a single bond is a group. So there's 4 of them. So how do 4 groups move as far apart from each other as they can? Well, it's actually a little bit hard to draw, but I'm going to give it a shot here. They form a tetrahedron or a tetrahedral arrangement. Okay. So then what do? You say, well, wait a minute. One of them's a lone pair and another one is a lone pair. I'm just picking two at random. It doesn't matter which two you pick. You get the same answer either way. And then you've got hydrogen atoms on two of these, right? So remember, you got 4 pairs, 4 electron groups. 2 of them are lone pairs. So that's this one and this one. 2 of them are hydrogen atoms. So I'm just going to attach them there. So see what I did? I just drew the groups, 4 groups. 4 groups is tetrahedral. Why tetrahedral? Because that's as far apart as 4 groups can get from each other. That's just a geometric argument. So then the hydrogens are attached to 2 of those points. So what do we call that? Well, look. If you look at the arrangement, that's bent, right? It's like a little V-shaped and angular. Well, angular is a ridiculous name because angular could mean any angle. So I don't know why they would call something angular. So you get a little V-shape, which is called bent. So keep in mind, this can be a little bit confusing. The arrangement of the electron groups is tetrahedral, but the arrangement of the atoms is bent. And when we talk about Vesper theory, in the end, we want to know the arrangement of the atoms. So our answer would be that water is bent, okay? And then you just memorize that chart, bent 104.5 degrees, okay? Let me show you another one. So let's take, for example, no, I don't want to BF3, remember BF3? Yeah, I guess you could do, let's do BH3. Okay, that's called borane, BH3. Boron is in the center, and there are 3 surrounding atoms. And if you go through the electron calculation, boron has 3 valence electrons, hydrogen has 1, so you have 6 valence electrons. We've already used 6, we're down to 0. So what you do, I mean, really from a practical perspective, is you just say, look, 1 central atom, 3 surrounding atoms, no lone pairs. So then you go back to your chart, AX3, that's trigonal planar. And that's 120 degrees. So there you go. You've now answered that question. What is the geometric shape of borane, BH3? It's trigonal planar. It's 120 degrees. And then if you wanted to draw it, what they did in that one picture was they did this, right? There you go. So there's your trigonal planar. The angle is right here, 120. Remember, 120 is like a third of a circle, right? A circle is 360 degrees. So there you go. It's like a third of a circle. And then it's relatively simple, actually, if you just remember. But you have to know those charts. You have to know those 2 charts, list 1, list 2, and then you just sort of go through that. But again, that is what's minimizing the repulsion of these electron groups is 120. If you have 3 electron groups, a bond is an electron group, then to minimize that, it's 120 degrees. That's really what's driving the Vesper theory. Valence shell, so we're dealing with valence electrons, electron pair, so pairs of electrons, repulsion theory. Actually, in theory, it probably should be called valence shell electron group theory, because it's not the pair that's repelling, it's the actual groups, because a double bond behaves the same as a single bond. So let me see if I can find a couple of Alex problems here and show you. Here we go. Okay, so here's one. Predicting bond angles in molecules with 1 central atom and no octet rule exceptions. Okay, so no exceptions to the octet rule. That makes it a little simpler. COCl2 is phosgene. Okay, so it's phosgene, COCl2, which is a dangerous molecule. COCl2. So the way we're going to deal with this is we're going to start with the Lewis structure, right? And we want to know the angles. So let me come over here. Okay, so carbon in the center. So again, this all starts with drawing the Lewis structure. Okay, remember what we said before. If you have carbon, put carbon in the center and put everything around it. Okay, so now you count up your valence electrons. I keep calling it phosphorus. Carbon has 4, oxygen has 6, and then chlorine has 7. So that's 24. We've already used 6, so we're down to 18. So again, you take the surrounding atoms, get them up to 8 till you run out of electrons. If you have any remaining electrons, you put them on the central atom. Now the carbon only has 6, so which one are we going to pick to form the double bond? That's actually an interesting question. Which one is going to form the double bond? The way we would actually answer this question technically is we would do formal charge calculations. If you do the formal charge calculation, the formal charge here is 0. This one is -1, and this one is 0, right? You take valence electrons minus all the electrons in the lone pairs, and then minus the number of bonds. And what you get are these formal charges. So what happens is it turns out the oxygen is the one that's going to donate the pair of electrons, because by doing the oxygen, its formal charge goes down to 0. So we're going to make the argument that oxygen has a tendency to form double bonds, whereas chlorine doesn't, because chlorine has a formal charge of 0 when it has a single bond, and oxygen has a formal charge of 0 when it has a double bond. So that would be our preferred Lewis structure. The next thing we do is just go ahead and start counting things up. You've got a central atom. You've got 3 surrounding atoms. Now notice, even though we have different types of surrounding atoms, oxygen and chlorine, we treat them all the same in the Vesper theory. There is a slight variation in angles, but we don't need to worry about it. So if it's hydrogen or oxygen as a surrounding atom, just count it as an X. How many lone pairs are on the carbon? 0. So it's just AX3, which is trigonal planar, which is 120 degrees. So the answer is 120 degrees. It just wants to know the angle between the carbon chlorine bonds, okay? So carbon chlorine bonds, what they mean is the angle from here to here. But again, if you look at that Lewis structure, that doesn't look like 120 degrees. It looks like 180, but that's because Lewis structures do not give you the angle. You have to implement the Vesper theory in order to get the actual angles. So that starts here by counting up the number of surrounding atoms. So a more accurate depiction of what this looks like would be something like this. The oxygen would be up here and the chlorines would be down here, and that would be your third of a triangle, which would be 120 degrees. That's your trigonal planar. Okay, let's take a look at another one. Okay, let's try this one. Predicting bond angles in molecules with one central atom. Okay, what's the angle between the sulfur oxygen bonds in sulfur trioxide, SO3 molecule, SO3? Okay. Sulfur trioxide. Okay, so we start with the sulfur in the center. We have 3 surrounding oxygens. No charges. It's not SO3 -2 or anything like that. It's not an ion. If it is an ion, that's fine. You're just going to have extra electrons in the valence shell. Just do it the same way. So let's count up electrons. 6 for sulfur, 6 for oxygen, that's 24. We've already got 3 bonds, so minus 6 is 18. Again, you draw them as pairs around the surrounding. I'm stopping with 3 lone pairs, right? Because that's going to give each oxygen 8. Then pick one of them. Obviously, this is a molecule that would have resonance because you have 3 surrounding oxygen, so each could donate an electron pair for a second bond. But it doesn't matter for this. We're not trying to figure out whether there's resonance. We're trying to figure out what the shape of the molecule is. Oops, sorry. There's a double bond there. Here we go. There we go. So there we go. Octet rule for everything, right? So what do we have here? We have 1 central atom, 3 surrounding atoms, no lone pairs. Well, again, that's trigonal planar, right? That's 120 degrees. So there's your answer, 120. So really it looks something like this. There's the angle they're talking about, 120 degrees. That's a nice flat molecule, SO3. Okay. Let's see. Let's try one more. Just wanted to find one that has a different shape. So this one is a carbon-sulfur bond. So what is the angle between the carbon-sulfur bonds in the carbon disulfide CS2 molecule? So there's your formula, CS2, okay? Again, 1 carbon, 2 sulfurs. So you draw the carbon in the center. Count up your valence electrons, 4, 6. We've already got 2 bonds. Arrange them on the surrounding atoms first. There you go. And then here's what happens. The carbon only has 4, so we're going to actually need more than 1 bond. So there's 1. Right? But we need a second one, right? Because now the carbon only has 6. But by giving it 2 bonds, so what I'm going to do, I'm going to push this one over. Now, why did I do 1 from each and not like a triple bond? You could, but that would probably not be a very good Lewis structure. Here's why. Suppose you did a triple bond. So I did, another bond over here. Again, it comes down to formal charge. So, where the double bond comes from and whether it's a double or a triple or a single, that really gets into formal charge. What happens here is if you do the formal charge for sulfur, it would be 6 minus 3 minus 2, so that'd be plus 1. And then for this sulfur, it would be 6 minus 1, so minus 1. So you got these formal charges of plus 1 and negative 1. If you look at this one over here, 6 minus 4 minus 2 is 0. 6 minus 4 minus 2 is 0. So remember we said, you want to have 0 formal charges if possible. So the double bonds, the symmetry here, a double bond to each sulfur, that's what's going to give you a formal charge of 0. So this would be our preferred Lewis structure here. Okay, this one's going to be a little bit less stable here because you've got these formal charges. Nature seems to want formal charges closer to 0 if possible. So now, what do we have? We have a central atom, 2 surrounding atoms, no lone pairs, right? So this is not bent. If it had lone pairs, it would be bent, but this is linear. You just have to memorize that table. The 2 tables, right? The one with AX2, AX3, AX4, AX5, AX6, linear through octahedral, and then the second chart, second list was AX2E1, AX2E2 is bent, AX3E is trigonal pyramidal. So it's linear. And so actually this is a case where the Lewis structure actually kind of looks like the shape, but I'll draw it out here anyways. There's your 180 degrees. They're asking you for the angle between the carbon and the sulfur, meaning what's the angle as you go across the carbon, okay? Moving it across here. 180 degrees, half of a circle, right? Circle is 360, so if you go from here to here, that's 180. All the way around would be 360. Okay, so there's your answer right there. Okay, let's see. Okay, before I get to that one, let's do the ones with small organic compounds. Well, this is kind of interesting. Predicting bond angles in small organic molecules. So here they're actually going to draw you the Lewis structure. So that's kind of nice. They give you the Lewis structure. They just want you to figure out what the angles here. But be careful. Don't use the angles that they look like in these pictures. Those are Lewis structures. Lewis structures do not generally show you the angles. They're just showing you the arrangements of electrons. So you have to figure out what the angles are based on the Vesper theory. AX2, AX3, AX4, so forth and so on. So the actual molecule in this Lewis structure says, note for advanced students, give the ideal angles. Don't worry about the small differences that the ideal might be caused by the fact that there's different electron groups. So that point at the bottom means don't worry about small details. So for example, it turns out a lone pair takes up more room than a bonding pair. So if you have lone pairs, that tends to cause the atoms in the molecule to squeeze a little closer together. So, you know, it'll go from 109.5 down to 107 if there's one lone pair. If there's two lone pairs, it'll go down to 104.5. So just, you know, just worry about those primary angles. So linear 180, trigonal planar 120, tetrahedral 109.5. Okay, so let's do A first. So here's what you do with A. So we're talking about the around, see these bonds are both on this carbon, right? So like this bond is on this carbon, but it's not on this carbon, right? This carbon's not attached to this bond. This right here and this right here are both on that carbon. So all you do is you say, okay, what do we have with this carbon? There's no lone pairs. So it's AX1, AX2, AX3, three surrounding atoms on this carbon here. AX3, no lone pairs, is trigonal planar. Trigonal planar is 120 degrees. So we would expect this to be 120. Now angle B is for this carbon. So what is it attached to? This carbon has one surrounding atom, two surrounding atoms, three surrounding atoms. So that's AX3. AX3, no lone pairs. AX3, again, trigonal planar, 120 degrees. Okay, so angle B would be 120. Let's come up and do another one. That one's actually, well, that one's a little different, right? Okay, so let's do this one right here. So this actually be the same here. So angle A is around this carbon. It's AX1, X2, X3. Those are the attachments. Three surrounding atoms. Again, it doesn't matter if hydrogen is a different atom than carbon. It's a surrounding atom from the perspective of this first carbon, C1. So three surrounding atoms, that's AX3, no lone pairs. Again, trigonal planar 120 degrees. But now we're doing around this nitrogen. So the nitrogen has one surrounding atom, two surrounding atoms, three surrounding atoms. So that's AX3, but it also has a lone pair. So that's AX3E1. And what we said with AX3E1 was AX3E1 was 107 degrees. Okay, 107 would be the angle for that one right there. Now let me see if they actually have you do 107. Okay, so they're actually going to say this. I'm going to show you the answer here down at the bottom. See how they make it 109.5, not 107? That's that issue there. Don't worry about the electron groups having slightly different sizes. So for these problems, what they're telling you is the bent, which is 104.5, just call it 109.5. The Trigonal Pyramidal, which was 107, just call it 109.5. So it really, I mean, really it's 107 degrees, but that's fine. Just call it 109.5. So bent and trigonal pyramidal, which are slightly different from 109.5, for these problems, just call them 109.5. Okay. So let's come back over here. Let's look at one more. Okay, that one, you know, to be honest with you, that one looks the same. That one's not any different. So I want to find one that's a little bit different. Here we go. This one's a little different. So let's do A. A is the same. You have a carbon with a double bond. So there's 3 surrounding atoms on this carbon. No lone pairs. So that's AX3, trigonal, planar. But this oxygen is interesting because angle B goes around that oxygen. Here you have 2 surrounding atoms and 2 lone pairs. So there's your AX2E2, which I would have said is 104.5, right? That's bent. But again, they're saying don't worry about that slight difference. Just call it 109.5, the tetrahedral arrangement, because they're really just looking at the, you know, the theoretical angles that you would have here. Okay. It turns out the lone pairs they take up more space, so they squeeze the hydrogen and the carbon a little closer to each other, so they become 104.5. But for this one, they just want you to give the 109.5. Okay. Let's see here. Okay. And last one from this section is we're going to give the name of the shape that corresponds to these arrangements. So let's look at the first one. Answer these questions in the table below about the shape of the xenon tetrafluoride XeF4 molecule. What 2-word phrase best describes the shape of the XeF4 molecule? Xenon tetrafluoride. Okay, well, again, the way this works is you got to draw the Lewis structure and then figure out where on those 2 lists it shows up. So this is an interesting one. I'm going to go over this one in detail because it's actually an interesting molecule in terms of being a noble gas. We don't normally think of noble gases as forming compounds, but it turns out that if you put a lot of effort into it, you can get these noble gases. Not all of them, just krypton and xenon. You can get them to form chemical bonds with highly electronegative elements like fluorine and oxygen. Really, I don't know that anybody's done it with nitrogen. So let's take a look, XeF4. So what you do is, again, you just start off this way, XeF4. Okay, count up your electrons. Now, what happens with xenon is it's in group 8A, and fluorine is in group 7A. So you got a lot of electrons, 8 for the xenon, 7 for the fluorine. What is that, 32? 36. Let's see, 7 times 4 is 28, 36. We've already used 8. So that gives us 28. So just put them on the surrounding atoms to get them up to 8. But what you're going to find is that you're still going to have 4 left over. So they got to go on the central atom. Right? So you fill out the surrounding atoms. And then if there's any extra, you put them on the central atom. Now you could say, well, wait a minute, that's a lot of electrons around the xenon, but that's right, because xenon already started with 8. It's forming some bonds here. Do the formal charge calculation for xenon and you get 0 here, because it has 8 minus 4 is 0. So it's got a good formal charge. Okay, so this is the one that we talked about earlier. It's AX4 E2. And that one was called square planar. So how they said, call it the 2-word name, square planar. That's 2 words. And then what's the angle? 90 degrees. Okay. So that one's kind of a cool one. The angle is 90 degrees. That's your square planar. Let's do one more. Sulfur hexafluoride, same thing. It's either a 1 What word or two-word phrase? So, you know, the names are not 3 words. They're either 1 or 2. SF6. Okay, so, and then what's the angle for that one? Something degrees. Okay, this one's relatively simple. It's not that exotic. It's an interesting molecule. Sulfur hexafluoride is an interesting molecule. It has certain industrial uses, but it's also intense infrared absorber, so it's got a problem for global warming. Sulfur in the center. Now, when you have that many surrounding atoms, what I tend to do is I draw it like this. Okay, because it's not going to fit in a simple box when you got 6. Okay, sulfur has 6 because it's in group 6A. Fluorine is in group 7A, so it's got 6. I mean, sorry, 7. I'm sorry. Let me write it this way. Confuse myself with these numbers. There's 6 fluorines and each one has 7. So that's 42 plus 6 is 48. But we've already drawn in 6 bonds, which is 12. So that gives us 36. Now this one, it actually works out perfectly that if you put 3 lone pairs on every fluorine atom, you get 36. 6, 6, 6, 6, 6, 6, 36. And there you go. Okay. So what do you have? You have A, X6, no lone pairs. That's octahedral. Right? That's from that list. And then there's 2 angles. No, I'm sorry. There's only 1 angle for it. It's 90 degrees. I'm sorry. I got excited there. It's the Trigonal Bipyramid that has 2 angles. It's 90 and 120. But for the octahedral, it's just 1 angle. It's 90 degrees. Okay. So there you go. There's that one. Let's see, there any others? So for that particular problem, they seem to give you, you know, slightly more complicated ones. Okay. Let's see. Yeah, that one's cool. I'm going to show you one more because this one I was just looking at. This one, this is kind of one that I didn't really show you before. So let me show you this shape too. So this is Xenon Difluoride. Okay. Again, a relatively exotic molecule. Not something people work with on an everyday basis. XCF2. So again, you got this noble gas. So let's take a look at it. XCF2. Okay, so xenon in the center. 2 surrounding atoms. Now you count up all your electrons. 8. Remember, this is in group 8A, so it's got 8. Fluorine's in group 7A, so that's 14 plus 8 is 22. I've already used 4, so that gives us 18. So you get, this is weird, you get 3 lone pairs. So I'm going to draw it like that on the central atom, okay? This is one that I didn't put in that list, so I did want to show this one to you because it's a little different. When you have this, so this is really AX2, E3. Ooh, what is that one? Okay, so here's the argument we'll make. Essentially what happens is you get the central atom, which is a xenon. So let me just write it as xenon. And really you have 5 attachment points. You've got 3 lone pairs and you've got 2 surrounding atoms. So that's 5. So what is that? That's actually like a trigonal bipyramid, right? When you have 5. But what happens is, see how you have 2 surrounding atoms and 3 lone pairs? What happens is apparently the lone pairs, they preferentially go to these positions here on the equator. Those are the equatorial positions. And the surrounding atoms go on the axial positions right there. So again, the shape of the molecule is the arrangement of the atoms, not the lone pairs. So if you look at that, you get a straight line. So the trigonal bipyramid is the arrangement of the electron groups, but the actual shape of the molecule is 3 atoms. XCF2 is actually linear, and linear is 180 degrees. So that would be your answer for that one. It's kind of interesting. So the shape of the atoms is the shape you're looking for. So that was not on the list. We had AX2E2, AX2E1, AX3E1, AX4E2. Now we have one more, which is AX3E3, and this is your linear. And then this one was the square planar. And then this one was your trigonal pyramidal. And then this was your bent. And this was the bent as well. Okay, so there's an extra one there for that Lewis structure. I mean, for that arrangement. Okay, so that pretty much does it for all of those. Everything else in that section, 9.1, is pretty easy. You're just sort of counting up the electron groups. I'm gonna show you one more. Maybe we'll do this one here. So answer the question in the table about the chlorine pentachloride. Maybe this one we can even do without actually showing it. ClF5. Actually, you need the Lewis structure, right? How many electron groups are around the chlorine? So how many electron groups are around the central chlorine? Remember, an electron group is either a lone pair, a single, a double, or a triple, right? So a triple bond doesn't count as 3 groups. A double bond doesn't count as 2. They only count as 1. And then what's this arrangement? And then, you have a scroll bar. You can look at those choices. Okay. So ClF5. Again, you got to draw the Lewis structure first. So chlorine in the center. You got 5. 1, 2, 3, 4, 5. Let's draw that a little neater. Count up. Now these are both in group 7A. So 7 plus 5 times 7, 42. We've already done 10, so that's 32. So if you get good at counting by 6s, 6, 12, 18, 24, 30, right? You'll find that, hey, there's an extra 2 because it's 32, but putting 6 on each fluorine gives you an extra 2. So there you go. Okay, now this one is an interesting one. This one has 5 surrounding atoms and 1 lone pair. Right? So that's an interesting one. That one, again, is not one that I showed you before. But with this one, they just want to know the arrangement of the electrons. Okay, they don't want you to give the geometric shape for this one. They just want to know the arrangement of the electrons. So how many electron groups do we have? So you have 5. Well, actually, let's come back. 1, 2, 3, 4, 5, 6. So you have 6 electron groups. And the general arrangement for 6 electron groups is octahedral. Okay. So in terms of electron groups, if you have 2, that's linear. 3, trigonal planar. 4, tetrahedral. Okay. 5, trigonal bipyramid. And then 6 is octahedral. Okay, there you go. Okay, so there you go. So that one, even though the shape of the molecule is not one that we've gone over, they're not asking you for the shape of the molecule. They're just asking you for the shape of the arrangement of the electrons. So just to show you what this kind of would look like. I guess we can do it using that wedge and dash line notation. So you got 5. So really then the question is, well, where does the lone pair go? The lone pair is most likely going to go up here. So you get this really kind of trippy looking arrangement. But in any case, they're not asking you for that arrangement of atoms. They're just asking you for the arrangement of the groups. 1, 2, 3, 4, 5, 6. There you go. Okay. So that is that section. I want to take a moment to look at section 2, okay, which is called, which is called polarity. It's called molecular polarity. Okay. And so with this one, what they're going to have you do is they're going to have you predict the polarity of a molecule. So that requires a little bit of review. Remember back in chapter 8 when we talked about electronegativity? Right? That's central to this discussion. Okay, so I'm going to try to make this as simple as I can. Remember what we said? We said that if you had 2 atoms that are covalently bonded to each other, and there was a significant difference in electronegativity, so that would be a big difference right there, right? Oxygen is 3.5, hydrogen is 2.1. Let's remind ourselves. Fluorine was 4.0, chlorine was 3.0, bromine was 2.8. Iodine was 2.6. Those are the electronegativity values. Next to fluorine was oxygen at 3.5. Sulfur was 2.5. Then over here we had, nitrogen was 3.0. And phosphorus was 2.1. Carbon was 2.5. Next to that one was boron, which is 2.0. Okay, hydrogen was all the way over here, of course, at 2.1. So these are some of the important elements. What we said was that in a bond, if there's a difference in electronegativity greater than 0.4, that would be a polar bond. And so we said, hey, yeah, that's a lot bigger than 0.4. So we would have a negative charge on the oxygen and a positive charge on the hydrogen, but it would be a small charge, not like -1, -2, or +1, +2, but like maybe -0.3 or -0.4. So we put that little delta sign there, okay? So we determined bond polarity, right? That's what we would call bond polarity, right? But that's not the same as molecular polarity because molecules have multiple bonds in them. So the question then is, what's the polarity of a molecule as opposed to a bond? And I want to go through the geometry. This is really just a geometric shape. So if the bonds are polar in a molecule, okay, that's the first proposition here. First of all, if the bonds are not polar, the molecule can't be polar. But if the bonds are polar, there's the potential that a molecule can be polar. And here's essentially what happens. I'm going to compare H2O to, can't do CF2. BEF2. Okay, so for that one, I got to put beryllium here. Okay, so there's a second row. Okay, so beryllium is 1.5. Okay, so here's what happens. I'm going to draw the shape of the water. It's bent, right? Okay, and now what I'm going to do is I'm going to draw the shape of the beryllium difluoride. So there's the arrangement of electrons. And it turns out if you look at it, BEF2 only has, it's AX2, right? So this one's AX2. So it's linear, 180. And this one is bent 104.5. It's AX2, E2. Here's what happens. Fluorine has an electronegativity of 4.0. Beryllium is only 1.5. So you have polar bonds, right? That's pretty obvious. That's a big difference in electronegativity. But here's what happens. Electronegativity differences, or polarity, polar bonds, they add up as vectors. So you have a negative on this side and a positive on this side. And then the other bond goes like this. You have a negative on this end and a positive here. So those two bonds, the polarities actually cancel. It's vector addition, essentially, is what happens. So the beryllium fluoride, because those two vectors cancel each other, overall it's nonpolar. Whereas here, if you take a look at these two bonds, so there's your positive and there's your negative. There's your negative, there's your positive. Those two, when they add, you get something that looks like this. So you get a negative this way and a positive over there. So this one ends up being polar. So two molecules, which seem to have pretty similar structures, one central atom, two surrounding atoms, the water ends up being polar and the beryllium difluoride ends up being nonpolar. So here's essentially the idea. If each bond is polar, but geometrically the dipoles cancel, the molecule is nonpolar. Okay, so for example, BEF2 is nonpolar. So the shape is really what determines, to a large extent, the polarity of the molecule. And so I'll give you a list of the shapes in a moment. You've seen them before, but here's essentially the idea. We have this concept called a dipole. Okay, a dipole is what you have when you have two charges that are separated by some distance. This is called a dipole. Two poles, right? So it could be two, it could be opposite charges, or it could be the same charge. But that's called a dipole, okay? So that's essentially what you get when you have a polar bond, right? So if you have a polar bond, you have a positive charge here and you have a negative there. So that's a dipole. It's called a molecular dipole, right? But what happens with dipoles? Dipoles are what are called vectors. Let me write it this way. Dipoles obey vector arithmetic. Vector arithmetic. Now, what does that mean to say vector arithmetic? It's relatively simple. The idea is if the vectors are pointing in the same direction when you add them, you get simple addition. So if they're pointing in exactly the same direction, you get simple addition. Okay. If they're pointing in opposite directions and you add them, they cancel. So you get 0. They're gone. Okay. Now, if they're, kind of pointing in the same direction, but not exactly, then it's a little bit more complicated. Then what you do is you break it down into X components and Y components, and you add the X components and you add the Y components, and then you get what's called a resultant vector. But we don't need that for some of these. We don't need them. So here's what happens. When we do the beryllium fluoride, what you get is this one's negative, right? Because it's more electronegative. This one's positive because it's less electronegative. So you have two vectors, right? You have two dipoles. So each of these is a dipole. The notation we use is that the head of the arrow points in the direction of the negative. Okay, so I'm putting the head of this arrow underneath the fluorine because the fluorine is electronegative. And then the tail, you can put a little cross there to remind yourself that it's positive. The tail of the arrow goes next to or coincident with the electropositive element, the one that has a lower electronegativity. Okay. And likewise, it's obvious if they don't have a difference in electronegativity, you can't add 0 and 0 and get anything other than 0. So there has to be a difference in electronegativity. But now this bond also has a dipole like this. Okay. And those two dipoles are the same size. They're the same magnitude because they're the same elements involved in the bonds. So that's essentially what you're getting then is they're pointing in opposite directions. So you have this, so you get 0. So overall, the molecule is nonpolar. It's a fascinating thing. You can have polar bonds, but the way those vectors add up, you can end up with a nonpolar molecule. So some molecules are nonpolar, even though they have differences in electronegativity. Okay. The water molecule is an interesting one because what you get is this. And so you get, this is the negative, this is the positive, this is the positive. Okay. So here, let me draw it like this. What you get is you get the first vector on the left looks like this, right? So you have the negative here and the positive down there. And then the second one looks like this, right? So they're not exactly pointing in the same direction, but they kind of are, right? So in this direction, they're both pointing upward. So what happens is, this one's going a little bit that way and a lot up. And then this one that's going like this is going a lot up, but only a little bit that way. So what happens is when you add them together, the X's are opposite directions, so they cancel, but the Y's are in the same direction, so they're additive. So your resultant is this. And it actually ends up being very, very polar because what happens is this one is pointing up, this one is pointing up there. So they're additive in kind of like this. So you get a large polar bond, a large polar molecule. So water is very polar. It's even more polar than the OH bond because those two are somewhat additive. Okay. So really then it comes down to the shapes. So you got to know what the shapes are. So I'm just going to give those to you right now. Linear, trigonal planar, tetrahedral, trigonal bipyramid, and octahedral. Okay, that's that first list that we did before, right? But I'm going to add to that, I'm going to add the square planar. Okay, these are all nonpolar. And it's like it's just geometry, right? If they're linear, they're going in opposite directions. The surrounding atoms are in opposite directions. If it's trigonal planar, now it's you have 3 coming off. Those cancel. Tetrahedral, all 4. All of those in that first list, they cancel out and they're nonpolar. Okay, even if the surrounding atoms have a different electronegativity than the central atom. And then what you get is when you do your bent and your trigonal pyramidal. So those are the ones, these are polar. These ones end up being polar. Okay, so this is your AX2 E2 or AX2 E1. And then this is your AX3 E2. I'm sorry, E1. Sorry. So really what happens is those lone pairs are really what make the difference. If they have the lone pairs, they tend to be polar. So this is your AX2 with no lone pairs, AX3 with no lone pairs, AX4 with no lone pairs, AX5 with no lone pairs, AX6 with no lone pairs, AX4 with 2 lone pairs, right? There's your square planar. Okay, so there you go. So now let's take a look at a problem. Let me give you a minute to think about that. So there's really only one type of problem in this section that we're working on, which is just to determine whether the molecule is polar or not, and then to determine which one is closest to the negative side. Okay, the more negative is the more electronegative element. Okay. Okay. Okay, decide whether each molecule or polyatomic ion is polar or nonpolar. If it is polar, write the chemical symbol of the element closest to the negative side. For example, if you're doing HCl, if the molecule were HCl and you decided that the hydrogen atom was closest to the negative side, you'd enter H, okay? So the first one is CS2. Now CS2, if you look up the electronegativity differences, there isn't any. Carbon is 2.5, sulfur is also 2.5. Maybe it's 2.6, but that's such a small difference in electronegativity. It's going to be nonpolar. So it's not a geometric issue with CS2. It's really just an issue of the electronegativity differences. You have to have a significant, at least 0.4 or 0.5 difference in electronegativity for something to be polar. Okay, so that one's nonpolar. Then you do the CLF. Now CLF, if you look at that one, you've got, it's only got 2 atoms. If you only have 2 atoms, it's going to be linear. Okay, but take a look. If you look at that one, is there a difference in electronegativity? Yes, chlorine is 3.0, fluorine is 4.0. So that is a big difference. So it's going to be polar. Then you say, okay, which one's going to be negative? The fluorine is more electronegative, so it's going to be the negative one. So F would be the negative one. Okay, but there's only 2 atoms. If there's 2 atoms, you don't have to worry about the shape because you know it's just those 2 atoms. You're just really there, you're just looking at bond polarity. And bond polarity between 2 atoms is just the difference in electronegativity. So that one, you don't even have to worry about the shapes. The last one is NH3. That one has a central atom with 3 surrounding atoms, 1 lone pair. So that's AX3E1. Now, nitrogen is 3.0 in terms of its electronegativity. Hydrogen is 2.1. So that's a big difference. That's a difference of 0.9. Then you have to go to the geometry. Okay. Trigonal pyramidal. So trigonal pyramidal, we said, that's in the second list. If it's in the second list and there's a difference in electronegativities, then yes, that one would be polar. Okay, so which one? The electronegative element is the nitrogen. So that's going to be the one that's closest to the negative side. Okay, let's look at one more. Okay, so we have CO2, I2. Okay, carbon and oxygen. Okay, there is a difference in electronegativity there, 2.5 and 3.5, 1.0. That's a big difference. So it could be polar. The bonds are polar. But then we have to go to the shape. So how do we do CO2? If you go through the Lewis structure and then the shape, you're going to find that it's linear. It's linear, right? So what do we say? If you have linear arrangement, the dipoles cancel. So that's going to be nonpolar. I2, only 2 atoms. So just look at differences in electronegativity. You don't have to do the shape if there's only 2 atoms. 0 difference, right? Iodine and iodine is the same atom. So there's no difference in electronegativity. So that would be nonpolar. Last one, CH4. Okay, well, there is a small difference between that 2.5 and 2.1.4. That's really sort of on the border of whether it's polar. However, if you go through the Lewis structure and the shape, the geometric shape using Vesper theory, you get tetrahedral. So tetrahedral was in that first list, so it would be nonpolar. So it turns out for this one, none of them are polar. They're all nonpolar. Okay. So that does it for section 2. It's really just that type of problem right there. Tomorrow, what I'm going to do is I'm going to talk about section 9.5 and 9.6. We're going to look at hybridization And then we're going to look at 9.6, which is molecular orbital theory. And that will be it. There's 2 types of problems for the first one, 9.5, and then 4 for 9.6, and we'll be done tomorrow. Okay, so I hope everything's going well. Hope you're wrapping everything up. Have a great day, and we'll see you tomorrow.